So, good morning, everyone. So today I am going to tell you a bit about the applications of radio astronomy in the field of cosmology. So, as you will see, this is a very vast field. I mean, there are a lot of applications which uses radio astronomy in cosmology. So, what I will do is I will try to give you a kind of broad overview of cosmology so that you all know what I'm talking about, and then I will pick out two, three very special cases, which probably is what I like, and then tell you how radio astronomy has played and is still playing and going to play a big role in the field of cosmology. So cosmology, I mean, again, all of you would know some bits and parts of it, that we are living in an expanding universe, and cosmology basically is the study of our universe at the largest scales. I mean, so we are trying to study the universe in its entirety. How, I mean, it got formed, how it's evolving, what may happen in the future. And modern day cosmology is basically based upon a series of observations, and probably the most prominent of that is what we call the Hubble-Lemaître law. Basically, distant galaxies are moving away from us, which gave rise to this concept of expanding space. Not only they are moving away from us, it turns out that the speed of recession is proportional to the distance to the galaxy. So which means if there is a galaxy which is twice as far away compared to some other, it will move away with twice the speed. And this kind of special linear relation leads to the model which we have for our universe. The fact that it is this proportionality tells us also that this expansion can be characterized by just one function. We call it the scale factor A of t. So A of t is a function which is expanding with time. Now, how it is expanding will depend on what the universe is made up of and what is the curvature and so on. But it is an expanding function, and the way it is normalized is that we say it is 1 today and it is less than 1 at earlier times. And if we go back early enough, it's probably very close to 0. Now, because of this expansion, something important happens to photons traveling in the universe. And of course, I mean, since you are doing astronomy, in particular radio astronomy, I mean, you will be thinking about radiation throughout. So let us then quickly understand what the expansion does to the radiation. The wavelength of the light, as it traverses through this expanding universe, expands just like the scale factor. So if the size of the universe doubles, the wavelength of the light will also double, and hence the frequency will become half. So this is called redshift of light because the wavelength is increasing. Now, since the size of the universe is characterized by the scale factor, what you can do is you can immediately write relations which will relate the redshift to the scale factor, because the redshift is essentially determined by the ratios of the wavelengths of the observed light and the emitted light. And it will turn out that this redshift, the quantity which we define as redshift Z, is basically 1 by A minus 1. Now, this is very significant because what you need to understand is redshift is something which is directly observable. So, if we observe a distant object, and if there are, let's say, spectral lines which we can identify very easily, and we know their wavelength in the laboratory frame, we can immediately find out what their redshift is. We may not know anything more about the object, but redshift is something which is kind of relatively easy to find out. Now, the earlier the radiation is emitted, more is the increase in the wavelength and decrease in the frequency. So from the redshift, we can immediately find out what would have been the size of the universe at that time when the radiation was emitted and is reaching us today. And then you can do a lot of things with that. So this basically outlines what I wanted to talk about. So redshift is something we observe. We can immediately find out the scale factor. This is just done. Now, once we know the scale factor, what we can do is, if we have a model of our universe, so suppose you know what the universe is made up of, and we know what equations, let's say, describe the universe. In our case, it will be the Einstein's equation of general relativity. You can immediately, since you know A, what you can do is you can solve for this function A of t, so that will give you the time. So the age of the universe when the light was emitted, or the time which passed between when the light was emitted and when it reached us. And because it is light ray and it will travel with a fixed speed, that will immediately give you the distance. So as a result, what happens is in cosmology, redshift plays the role of like time or age as well as distance. So we will talk about, so when we use sentences like we observe object at redshift something. So maybe we are thinking about something like time. Light is coming from redshift 3. So maybe we are thinking, using redshift as a proxy for distance and so on. So this redshift is something which is very fundamental in cosmology because it relates to both the age and the distance. By the way, if you have questions and if anything is unclear, do ask me anytime. Just stop. So, as we said, since at early times the galaxies were closer to each other, since the universe is expanding, clearly the galaxies were closer to each other at earlier time. And hence, the universe probably began from something like a point. It could be a very small volume. We really don't know what happened when the scale factor actually approaches 0, but it's clear that the universe would have been beginning from a very small point. So this gives rise to the present model of our universe, which is we call the Big Bang model. Okay, so the universe starts from a point and expands, and it reaches where we are. Because of this expansion, what happens is if you take let's say particles, and if you compress them to a smaller volume, basically the kinetic energy will increase, and as a result the temperature of those particles will increase. So that immediately tells us that at early times the universe must have been hot, much hotter than what it is now. So that is why often this Big Bang model is also called a hot Big Bang model, because it started with the universe which was like really hot. It can be as hot as you want if you go to early enough times. And this gives a very rough estimate of what could be the temperature. So when the age of the universe was of the order of a second, it would be something like 10 to the 10 Kelvin. It would be million Kelvin when the age of the universe was something like a year. And then it falls down as the universe expands. Now, because of this hot Big Bang, the fact that the universe was hot and then cooling, various interesting events happen. And I will again pick just one of them because that's probably something where radio astronomy plays a big role. What happens is if you go early enough, the universe would have been so hot that you won't be able to form atoms. In the sense, you won't be able to bind the electron to the nucleus, let's say a proton. Okay. So then, even if you try to do that, it will dissociate very easily. It's just because there's just too much energy in the universe. So you have to really wait for some time for the first atoms in the universe to form. And how much should you wait? So the current understanding is when the age was something like 380,000 years, let's say 400,000 years after the Big Bang, the energies would have been small enough so that protons and electrons can bind with each other. Now, so this is a rough picture which shows, let us say, there are protons and electrons which are free charged particles. What would happen is the light or the photons would constantly scatter off these free charges. So this would be before the atoms were formed. But after the atoms were formed, the universe became kind of predominantly neutral. So there are no electrons or free electrons or protons. There are electrons and protons, but they are now bound. As a result, the light cannot scatter so easily. So the light basically free streams. It's just moving through the universe. Its wavelength is changing, but it is just moving without having any significant interaction. Now, the question is, can this light be detected? Because this would be a very good proof of the model we are talking about. And it turns out that yes, this is basically the light which we call the cosmic microwave background radiation. And this was detected in the 1960s by people who were electrical engineers. They were using a radio equipment to do some other experiments, but they found excess radiation. This was kind of accidental detection in some sense. So yeah, so this was detected, and it turns out that actually the theoretical prediction for this existed well before that. In the 1940s, 50s, people like George Gamow and all, working with the expanding universe and the fact that it would be hot at earlier times, they could work out that the universe would be filled up with a bath of radiation. And not only that, because the photons were getting scattered off electrons, equilibrium would be established, and that would lead to a radiation which has almost perfect black body. So there was a prediction that the universe will be filled up by a black body radiation. And now once the universe becomes neutral, this black body radiation just comes to us. And what happens is its frequency goes down, the wavelength goes up. As a result, the temperature goes down. And the fact is, that is the thing which was detected by Penzias and Wilson. Later on, satellites were sent to kind of confirm, for example, the spectrum of this signal. So this was done in 1990s by Kobe. And they found out that indeed there is the spectrum is indeed a black body. So so this shows the data points with error bars, but these error bars are magnified by 400 times. Okay, so otherwise you won't be able to see that. And this is not a fit to the data. This is just a 2.725 degree Kelvin black body, and you can see how nice it matches. So this is kind of one of the most perfect black body we have in our universe. That's the cosmic microwave background radiation. Its temperature today is something around 2.73 Kelvin. Of course, when it started at early times, that time its temperature would have been higher. Okay, so it would be something like of the order of 3000 Kelvin, and then it cooled down, and it has today we are observing at something like 3 Kelvin or something. So this 3 Kelvin black body, the spectrum basically peaks at microwaves. That's why the microwave name comes. And this is something, if you think about it, this is something where we are really talking about frequencies which are kind of the higher end of the radio spectrum. So the CMB is one part where really radio astronomy provided a big kind of contribution to cosmology. and I will talk a bit more about it soon. Now the CMB is itself very interesting. If you observe the CMB, now the you let's say hypothetically, you are observing CMB in different directions. At different directions, you are taking the spectrum, and let's say you are measuring the temperature. It turns out that this temperature is extremely homogeneous, or you can say isotropic. It looks the same no matter which direction you look. So this essentially tells us that the state of the universe was extremely smooth when the CMB originated. That's why it's like the temperature is same no matter in which direction we are looking at. Of course, so which means that the matter in the early universe was extremely smooth. This is coming from the CMB. And as I said, the CMB reflects the state of our universe 400,000 years after the Big Bang. Just to understand what this 400,000 years means, the age of the universe today is something around 14 billion years. So we are really talking about very early times in our universe. However, if you now go and observe the same CMB with very high resolution experiments, you will find that although it is extremely smooth, there are some fluctuations, and these fluctuations are really small. If you don't have a sensitive enough instrument, you won't be able to detect this. So we are talking about 1 part in 10 to the 5. Okay, so this is the kind of fluctuations one sees in the CMB, but they exist. So this tells us that there were, the universe was extremely smooth there, but there were tiny fluctuations at those times. The matter in the universe was not like fully smooth. We really don't know how these fluctuations actually were formed, but maybe because of some exotic physics at very early times. These anisotropies were first observed by Kobe itself at a very crude level, but later improved by other satellites like WMAP and Planck. Okay, so these are the kind of state-of-the-art results we have of CMB. This is also complemented by several ground-based telescopes. which basically probes the small scale anisotropies. Now, that was the CMB. So, early universe, smooth, tiny fluctuations. What about the universe today? So, the universe today is best kind of probed, at least at the cosmological scales, by, let's say, galaxy surveys. So, observations of galaxies. So, this is, for example, one galaxy survey. So, each point here is a galaxy. So, this is basically the distance from us, which also corresponds to the redshift. Okay, so, this distance or redshift, and this is one slice of the sky. So, you see that the galaxies which are observed by these surveys are shown as points here. And you can see they are not kind of randomly distributed. There are kind of structures, in the sense there are places where there are a lot of galaxies, and then there are places which are voids, and I mean these collection of galaxies are sometimes connected by a kind of filament like structure and so on. So you can see there is a lot of rich structure, and these are called a large scale structure of the universe, or sometimes they are also called cosmic wave. And the problem of large scale structure formation in our universe, so one of the problems in Big Bang cosmology is how did these rich structures form from the almost very homogeneous kind of universe. So 400,000 years age, very homogeneous. Today, extremely rich structures. Okay, so something has to happen for these structures to form. We understand what has happened. This is something called gravitational instability. But getting the results right quantitatively is something which people who study large-scale structure formation always do. Yeah.
So what were the different colors which are represented?
These are different types of galaxies, basically. Okay.
So like orange represents what basically?
I don't remember. I mean, these are probably color of the galaxy. So the orange would be the red galaxies, and the blue ones will be what we call blue galaxies. Okay. So, yeah, this depends on the spectrum of the galaxy.
Whether they're like red means like is it a Doppler or not?
No. They're intrinsically red. Okay. So this would be okay. So this would be basically two different types of galaxies. So the way we understand is red galaxies are the ones which have already gone through star formation as kind of dead today, and the blue ones are star forming. Okay. Now with all these things, we now have a model of cosmology which we can call the standard model of cosmology or the concordance model of cosmology. So just to summarize what we were talking about till now, is there was a Big Bang, then the universe kind of expands. So initially there is a phase of inflation which I did not talk about, and then the universe as it expands it cools. So at some point the protons form, because earlier even forming protons would have been difficult. This is just too much energy. At some point, a nuclear fusion begins. So basically, you can form some non-trivial nuclei. Then comes what we were talking about, the atoms form, and cosmic microwave background basically originates. Then we enter a phase which we call dark ages. Basically, during the dark ages, the universe doesn't have any like luminous sources, because the galaxies haven't formed. The universe is just too smooth to have any galaxies formed and so on. So these are called dark ages. At some point, the first stars and the galaxies form. So these are this phase is called cosmic dawn. This is followed. I mean, and I will talk a bit about it later. And then we enter a phase which is modern universe, which is dominated by the galaxies we see. So this is the rough history of the universe. And if you keep this picture in your head, it will be easier. Now, radio astronomy actually provides a lot of input to various stages in this picture. And these are some of the things which I have listed, but there are many others, and maybe even during the other lectures you will realize where radio astronomy kind of provides inputs to the large scale universe. So one place where radio astronomy is crucial is for studying like high redshift galaxies. These could be various properties of the galaxies, and this is something I will talk about, angular size flux relation of radio galaxies. The high redshift galaxies can be used for studying what we call the large scale structure formation. Just like you have that galaxy surveys, the picture I showed, that was of course the optical galaxy survey. But similar things in principle can be done for radio galaxies as well, and you can then study the clustering properties of those. Then tests of statistical isotropy. So we think that our universe is statistically isotropic. Okay, that's the model of our universe. But is it indeed true? So people go and look at like surveys of radio galaxies, and there are, for example, claims that maybe there is some violation of statistical isotropy. But it is not clear whether that is true, that's indeed true, or there are systematics still in the data which is not taken care of. But these are places where the galaxies which are bright in radio play a role. And then there is something which is probably becoming and may become important, are what are called fast radio bursts. So these are basically very energetic events happening at cosmological scales in galaxies at very distant universe. Whether they can be used for cosmology or not is something I can't answer now, but they look very promising. So once a lot of statistics is built of this fast radio burst, I'm sure there will be cosmological applications of them. But this is a very new field which is kind of building up. Then CMB, which we talked about, and I will talk a bit more about them in terms of fluctuations. And then, of course, the spectral distortions from the black body spectrum. So CMB is almost perfect black body, but as the photons are traveling from that time to us, it's not like they don't interact at all. There are interactions with other stuff, okay, other atoms and things like that. And some of these will lead to deviation from the black body spectrum. And I will again spend some time on it in the later part of the talk. And then, I mean, related to this is something called 21 centimeter cosmology, and then again, something I will talk about. So let me just quickly talk a bit about this angular size flux relation. So imagine there is a radio galaxy having a luminosity L and some size small l, okay, at some large distance, okay, and you see I'm using redshift to tell that it's some large distances. Now, if it has a luminosity L, the observed flux will be luminosity by 4 pi distance square. In cosmology, again, defining distance is a non-trivial thing. So in this case, we will use something called luminosity distance. Don't worry what it is, okay? Just think. Now, you can also, there will be observed size, observed angular size of this object. That is called theta. That will be L by, again, distance. This distance is not same as that distance. In a non-expanding Euclidean universe, these two distances would be identical. But in expanding universe, there are non-trivial effects which make these distances not equal to each other. But, so what I'm trying to say is, if there is a radio galaxy which has a luminosity L and some size L, you can infer about the luminosity through the flux. You can infer about their size through the angular size theta. Now, if you have some model of radio galaxies, for example, how this luminosity and size varies with redshift, that will basically define, give you a definite relation between this angular size, which is observable, and S, which is also an observable. So you go and observe the size of the galaxy, you go and find out how much flux you are receiving, and make some kind of a plot. So these are those plots, theta versus this flux S. And the points with the error bars are the data. And given a model of radio galaxies, or how these things evolve with time, there will, I mean, that will predict a definite relation between theta and S. Now it turns out that if you just assume that this L, the size and the luminosity don't vary with redshift significantly, it becomes very difficult to fit the data. So this n equal to 0 points are something where the model has no redshift dependence. In the sense, the properties of the galaxies are same no matter at which state of the universe you are in. Now, when these observations were being done in the 1980s and 90s, that time it was not clear whether Big Bang model was the model of the universe. There existed a competing model called steady state model. And in the steady state model, one expects these things to be kind of redshift independent through the zeroth order. And these observations actually helped in giving an indication that the steady state model is probably not the right model of our universe. This is one result I really like, because this came from something in India, the Ooty radio telescope, and this was happening in the mid 80s. So this was something I think very significant. Of course, after that, in the 1990s, Kobe went up, observed the CMB and so on. So of course, now we know that steady state model cannot match the observations. There's no doubt about that. But even before that, there were indications which were coming from radio astronomical studies. Okay. Now let's come to the large scale structure a bit. Okay. So when we study large scale structure, most of the time we try to study the correlation. I mean, we are trying to study the distribution. Okay, that the fact that it is not homogeneous, it's not random. So the way to do is that you can do it in the CMB in terms of angles. You can do in the galaxies in terms of positions. What you do is you take two points basically, let's say x and x plus dx. You find out the number of galaxies in x around x and number of galaxies around x plus dx. And then you do it for different pairs of x and x plus dx. So you just take this x somewhere else, take delta x. You can take the delta x to be same, but you can calculate this quantity as an average. I mean, you can do it at various places. This is called the 2-point correlation function. And the way this is defined, basically, I mean, this will give you basically the probability of finding a galaxy at a distance x and at a distance delta x from where you are over random. Okay, so if it is random, then this correlation will essentially tend to 0 if the distribution is random. If it is not random, you will find something non-trivial. Okay, so that is the quantity which is usually used for cosmological studies. What people do is people like to work not in the like real space or configuration space. People tend to go to the Fourier space. So you calculate this correlation function in the Fourier space, and Fourier space is just Fourier transform of this correlation function, and that's called the power spectrum. This, for example, is the power spectrum of like density fluctuations in the universe, and these data points are coming from various observations. So what has been this power spectrum is usually studied as a function of wave number k. This wave number is such that it is inverse of distance. Now, which means small wave numbers will give you access to large scales, and large wave numbers will give you access to small scales. So these are small scales, these are large scales. At large scales, this power spectrum is essentially measured from CMB observations. At small scales, they are measured from galaxy surveys. Okay, so these are typical galaxy surveys, and there is something called Lyman alpha forest as well. This power spectrum is a very powerful quantity. It contains information on the primordial fluctuations, how did these fluctuations arise, and its subsequent evolution. And you can see the kind of standard model or the concordance model of cosmology is a very nice fit to all these data points. Okay, and these data points cover a wide range of length scales, a wide range of observations, but nevertheless, it's a very nice fit. So this is the reason why we believe that the standard model of cosmology is correct. And again, the radio astronomy plays a role at large scales, where CMB is giving us this power spectrum. Now, CMB actually doesn't measure the power spectrum the way I had plotted. It actually measures the power spectrum as a function of angular scale, and then we use models to convert it into a power spectrum in the distance scale. So these are basically what has been plotted here is that power spectrum as a function of angular scale or let's say multipole moment. So again, these are large angular scales, these are small angular scales. And it turns out that this comes with a very typical feature. Okay, so it's almost flat, and then there are peaks, and this amplitude of there's a peak and trough, and so on. And their amplitudes are decreasing, and then they decrease and just become negligible. Yeah. And what is the angular scale? So angular scale. So what we will actually do is we will calculate this correlation function, but here we will do as a function of theta. Okay. So angular scale in this case is delta theta.
So the angular scale is like from the Earth itself.
So you are basically observing the CMB as a function of angles. Okay, on the sky.
Okay.
So you're observing either in this direction or this direction. So you take two directions and calculate this correlation function. And then you take in this case, since this is a kind of, this CMB is like something on a sphere, right? So in this case, Fourier transforms don't work. You have to take what is called spherical harmonic. You have to expand in terms of spherical harmonics, and you will get something which will be this angular power spectrum. Okay, so it's conceptually very similar to Fourier analysis, but it's done in Legendre, in terms of spherical harmonics, Legendre polynomials, and so on. So you see, this is that quantity, and what is being measured are the temperature fluctuations, and you can see the units are micro Kelvin square. And I said it's 1 part in 10 to the 5, hence like you have to go to micro Kelvin to measure the fluctuations, and these features are very peculiar of CMB. Okay, I mean, and that happens because of the fact that these photons are constantly interacting with protons and electrons, what we call a baryon photon fluid, and that leads to what we something like sound waves, okay, acoustic oscillations, and these are the peaks of these acoustic oscillations. But then those peaks damp and so on. So there's a lot of physics involved, but this is very well understood, and this is like the prediction of the concordance model of cosmology. So you can see it matches the data superbly well. Now these were about temperatures. What people have gone ahead and done is you can measure the polarization of the CMB. Okay, so CMB light will get polarized, and the problem is that the polarization signal is much weak. So what has been plotted here is again that angular power spectrum as a function of that multipole moment. These are the temperature fluctuations which were shown in the previous plot. These are different kind of polarizations. Okay, so this one is this is the cross correlation of temperature and E mode polarization. This is basically the E mode polarization. Don't worry what E modes are. Then there's something called B mode polarization. So these are different kind of polarizations which one can observe. But the point I'm trying to make is, because of these observations, this has really made the cosmological model extremely robust. Okay, there's very little like latitude to kind of come with something which is not the standard model of cosmology. Because if you try to do something, I mean somewhere, it becomes very difficult to match or explain all these observations and the observations I showed in the power spectrum plot together. Okay, so these fluctuations in the sky, basically, be it CMB, be it galaxies, so these large scale structures actually nail down the cosmological model to a very high degree of precision. So we are entering a phase of, we have entered a phase which we call, precision cosmology. Yeah, go ahead.
Sir, I want to know how this
CMB gets polarized. So what happens is the scattering between photons and the electrons is Thomson scattering. Now that scattering cross section has an angular dependence. The moment the scattering cross section has angular dependence, it basically can give rise to polarization. There is just one subtlety here. It will give polarization only if the initial radiation field already has an anisotropy, a quadrupolar anisotropy. Okay, so which CMB does have. But essentially, I mean, the short answer is because of the Thomson scattering cross section. Okay, it has angular dependence, and that gives rise to polarization. Okay. Now we have entered the era of precision cosmology. Basically, we have the standard model of cosmology which can be described by 6 parameters. I'm not going into the details of the 6 parameters, but they are being kind of estimated with a very high degree of precision, using a variety of observations. So these are these various columns give you different kind of combinations of these observations. Again, don't worry about the details, but what I'm trying to say is the last decade or so has led us to this very very precise model of cosmology. Now, I mean, I don't know, fortunately, unfortunately, depending on how you look at it, it turns out that there are still unsolved issues, or there are issues which are coming up in recent times. So, for example, the universe is made up of components which are called dark matter and dark energy, and we have no idea what they are. Okay, so this is something which is, this keeps the model kind of incomplete. And this is something which is happening relatively recently, in the sense there is a quantity called Hubble parameter which characterizes the expansion of the universe. different experiments, when they measure the value of this Hubble parameter, are giving different values. And they are now kind of, the error bars are so small that they are kind of ruling out each other. Again, we don't know whether this model is going to break down at some point, or it still has to do some data, that the one or all the or more experiments still have some systematics which we don't understand. So this is something to keep an eye on. But yeah, now this model has told us what the universe is made up of, and basically we now know that almost 70% of the universe is made up of dark energy. We have no idea what this is, but this is a very exotic kind of quantity which seems to have negative pressure. About 26%, 27% is made up of dark matter. So dark matter again is like non-relativistic matter, except that they don't interact with electromagnetic radiation. So we cannot detect them in light, but we can infer of their presence through their gravitational interaction. If they are there, they will do what any gravitating matter does. And only 5% is basically ordinary matter. Radiation is negligible in present day, but earlier times radiation would have been significant. So this is the pie chart for the present day. The baryonic component, interestingly, is dominated by hydrogen. And hydrogen, again, is something which can be probed using radio. And I don't know, maybe people are already doing some experiments for this. So basically, this hydrogen is very well probed by the 21 centimeter line. And this originates because of the fact that the ground state of the hydrogen atom is split into two states, depending on whether the electron spin and the proton spin are aligned or kind of misaligned or anti-aligned. Okay, so this gives a small difference in the energy, and depending on whether the electron can go flip the spin, there will be emission. Now, the thing is, this 21 centimeter line probes the neutral hydrogen in the universe, because if you ionize, then the electron is not bound to the proton. So then there is no spin, there is no coupling between the two spins, and hence there is no 21 centimeter radiation. So the 21 centimeter radiation arises only when there is the hydrogen is neutral, basically. And it's a line transition. It originates at a particular frequency. The advantage is, if you observe that, and suppose you know that you are observing 21 centimeter radiation, but at a different frequency, that will immediately tell you the redshift. Okay, this is, for example, one way of calculating redshift of distant objects. It is what we call a forbidden transition. It's something called magnetic dipole transition. So its transition probability is extremely low. Okay, so an atom in the upper level is expected to make a downward transition in like 10 million years. So if you just leave a hydrogen atom, I mean, you won't see it. You won't have this transition in the lifetime. I mean, in million years. But since the universe has a lot of hydrogen atoms, I mean, this is kind of overcome because you just beat it by numbers. Now, a 21 centimeter radiation from galaxies allowed inference of, for example, dark matter. So it is very important. So let me skip this part where basically people observed flat rotation curves, and that gave us some idea about the fact that galaxies are surrounded by dark matter. And yeah, I'm just skipping it because I wanted to come to the next one, and I'm running out of time. The other place where 21 centimeter is going to play an important role in cosmology is, I mean, the other way to use it is to detect it from neutral hydrogen, not from specific galaxies, but like, as I was saying, the baryonic component is mostly hydrogen. So if you just look at this cosmic wave beyond the galaxies, the matter between the galaxies, they are also made up of hydrogen. So the question is, can we detect signal from there? So now we are going to, I mean, we are talking about the cosmological 21 centimeter signal, not the 21 centimeter signal from individual galaxies. Now here the idea is that there is CMB which is coming from whatever that earlier high redshift to us. And if there was nothing, we would have just observed the CMB. But the CMB photons may interact with neutral hydrogen, And if the frequency is right, what may happen is the neutral hydrogen atom may absorb a CMB photon and go from the lower state to the higher state. Lower state of this hyperfine levels. Okay, so it is still in the ground state, but its spin basically flips and it absorbs the radiation. Or it spontaneously kind of spin flips and radiates. So then you will add something to the CMB. So what can happen is, as the CMB is coming, if there is neutral hydrogen in between, you may get more light than what was there in the CMB, or you may get less light than what was there in the CMB, depending on whether these atoms absorb or emit. Okay? Whether they absorb or emit will depend on what is the level population, whether there are more atoms at the higher level or most of the atoms are already in the ground level. Okay? So all these things can be worked out and you will get a resultant kind of CMB and you observe that. So essentially what you are now going to observe is the deviation from the CMB, and this is what I was calling spectral distortion. So see, the black body will tell you that at a given frequency exactly how many photons or how much radiation you are expected to receive. This one will violate that. It will either add or subtract something. So it will deviate from the black body, and that is something one is trying to detect. And from that we want to learn about this cosmological distribution of neutral hydrogen in the universe. So that is the plan. The thing is okay. So as I said, the 21 centimeter line basically will allow study of several different aspects of cosmology and galaxy formation. And you can probe a wide range of redshifts using this 21 centimeter line, since its rest frame wavelength is 1420 megahertz or 1.4 gigahertz. So as it gets redshifted, it will go to lower and lower frequencies. So depending on how much access you have to lower frequencies, you can go and observe higher and higher redshifts and earlier times. Okay? So clearly, if you want to observe this 21 centimeter from a galaxy which is nearby, there won't be significant redshift. You will use a frequency 1.4 gigahertz. But suppose you want to observe a galaxy at redshift 20, you would want to use a telescope, a frequency range of something like 70 megahertz, and anything in between you will use an appropriate frequency range. Okay? Now the signal can be probed in different ways. Either what you can do is you can say that I will observe a large region of the sky and just observe, try to detect the average signal. So that will be like the globally average value of the signal. And let us say we would like to detect it as a function of frequency, which is equivalent to detecting it as a function of redshift, hence as a function of age of the universe. And depending on how it behaves, we will learn about our universe. Or you can try to make a map of some region of the sky in 21 centimeter and detect the fluctuations basically. So that will tell us something more about the universe. Just like CMB, you can detect the globally average signal, that will be that black body. But then you can go and look at slightly like higher resolution, then you will detect all these fluctuations and that will tell you something more about the universe. So same thing can be done with the 21 centimeter. Okay. And a large number of low frequencies experiments are being planned. In fact, some of them are ongoing to study the high redshift universe. If I go and look at the global 21 centimeter signal, this is how a typical signal looks like. Of course, we don't have a clear detection of the signal, so this is just a model. What has been plotted here with the black line is the deviation from CMB. So if there was no neutral hydrogen, then it would be 0. 0 means it will be a perfect black body, CMB. This is basically giving you the deviation from that black body. And you can see the signal does various like funny things. Okay, there is absorption, then it goes up, again an absorption, then it goes to emission, and so on. All these have very interesting physics which one can go into. But one thing which you can see is there is one absorption signal which is very prominent. And this is happening just at the time when the first galaxies form. Okay, so this is the time in this model the first galaxies form, and this is where basically the signal appears. This is a very prominent signal, and lot of kind of instruments are trying to detect this signal. The advantage is the moment this signal is detected, we will know when did the first galaxies in the universe form, or the first stars in the universe form. So this is why it's very, very significant. And I mean, there is a bit of a backstory here. I mean, there was an experiment which claimed detection that something around 3-4 years back. That was an experiment called EDGES. But the signal was just too high to be explained by standard models of galaxies. And more recently, there is another experiment done by a group in RRI, Bangalore, which seem to have refuted that signal. So it's not clear. Most likely that signal is not detected yet. But then probably we'll have to wait for like more data in this field to see. But even if it is not detected, one would like to understand where it is. I mean, when it is detected, is it detected at this redshift range with this amplitude, or is it detected at a different redshift range? That will then tell us that the first stars would have formed not according to what is predicted in this model, but somewhat different, and so on. Okay. Now, as I said, you can do a bit more. I can try to do fluctuations. So what has been shown here, what has been plotted here are simulations, because we still haven't observed it. This left panel basically gives you the large scale structure of the universe, the large scale density field. And as you see at earlier times, it looks very homogeneous. It's nothing here. But as time progresses, you will see that structures are forming. This cosmic web is becoming very prominent. You can see all these filaments. And these are the places where galaxies are formed. And then you can now see voids and filaments very clearly. This is a map of neutral hydrogen. And what you will see is that red ones are basically neutral and black ones are ionized. The moment you start forming galaxies, you see there it starts to ionize the surrounding media. Now this is very interesting because the universe was, because of hot Big Bang, the early universe was ionized because you were not allowing to form atoms. Then you formed atoms. That's where the CMB originated. But the moment the galaxy started to form, you start ionizing the universe again. Okay, so this is called reionization. And the good thing about reionization is this structure of these black regions or these ionized regions are exactly tracking the galaxies. Okay, so they are forming exactly where the galaxies are formed. And more galaxies you form, like more black regions are building up. Okay, so so one idea of kind of understanding the early universe is through the 21 centimeter radiation of this neutral hydrogen. Now, if you try to make a 21 centimeter map, it will look exactly like this. In the sense, wherever you have ionized, there won't be 21 centimeter from there. Wherever you are not ionized and neutral hydrogen is present, you will see 21 centimeter radiation. Okay, so that is the plan with the upcoming 21 centimeter interferometers. Okay, that they will try to observe these fluctuations and then tell us when the first galaxies formed, what kind of galaxies they were, how did they evolve, and so on. Now, of course, in this case, you will need telescopes which are kind of at relatively lower frequencies. We are talking about something around 50 to 200 megahertz. That is the phase when this reionization is most likely to happen. So one is talking about low frequency radio telescopes. And this gives you some like very, it is not at all exhaustive, some telescopes which are trying to detect this signal. So there are small radiometers which are trying to detect this global signal, and this EDGES is one. SARAS is the one which is done by the RRI group in Bangalore. And there are various others. And then there are interferometers which will help you in detecting the fluctuations. Okay. So there you need arrays. And we have MWL, LOFAR, our own GMRT. KIME and Meerkat are slightly higher frequencies, and they are trying to detect the post-reionization signal. And then, most of the time our interest has been this reionization phase. The signal is very weak because the transition probability is low. So it's possible that the current generation of telescopes may not be able to detect this signal. We may have to wait for the next generation of interferometers. And there are two which are very promising. One is the SK, in particular the SK low part, which will come up in Australia. And there is something called HERA, which is being built, and when it is completed, it will come up in South Africa. And both of them, one of their major science goals is to detect this 21 centimeter signal. Out of that, this SK has some special connection with India because it's a very large radio astronomy project which is being built in Australia and South Africa, and we expect the construction has just started like last week, and probably the first science will take maybe 4 to 5 years to happen. And India is member, India is part of this SK international collaboration. And GMRT is one of the what we call pathfinders for the SK. So it often provides kind of useful test bed for the SK. And once the SK comes up, hopefully we will have access to the telescope being part of that, and it would be very interesting. The thing which one is actually trying to measure is not directly these maps, because getting these maps would really take a lot of data. Rather, some statistical quantity like the power spectrum. Again, we are come back to this correlation function and power spectrum. So this is basically, this shows the value of the power spectrum as a function of k, same k. So these are small scales, these are large scales. And you can see as the universe evolves, as these black regions come up, this power spectrum does evolve, okay? It goes up, here it comes down, then this peak will shift, then it becomes flat, and then it vanishes because everything gets ionized, okay? So this is something one is trying to detect, this power spectrum, and because its shape evolves as the universe evolves, hopefully we'll learn a lot about these first galaxies and first stars once we have this power spectrum. This is the same plot, but plotted as a function of redshift for a particular scale. And as you can see, even if you just observe at one scale, it will evolve with a particular shape. And hopefully, once we observe this, it will tell us a lot about the early universe. We already have some constraints on this power spectrum. So this is the power spectrum for one value of k. So if you go back, this is basically that same k which I plotted here. So this is the plot equivalent to what was plotted here, but now with real data. So these are basically real data. What has happened is we only have upper limits because we haven't reached the sensitivity to detect the cosmological signal. In fact, one of the first upper limits came from GMRT in 2013, which I think sits here. But over time, all the other telescopes have taken a lot of data. They have various advantages, of course. And currently, the telescopes which are doing quite well are the Hera. This is just the preliminary version of Hera, which is here, MWA, and basically LOFAR, which is somewhere sitting here. So as time progresses, these upper limits will come down, and hopefully at some point we will be able to observe, detect this signal. With SK, even 100 hours, the noise is somewhere here, and hopefully that would allow detection of this signal without much difficulty. But with the present day telescopes, for example, with LOFAR, even 1000 hours may not allow us to reach the typical reionization signal. So that is all I wanted to tell you about. So this is what, these are some kind of bits and pieces where I think radio astronomy is going to give a very important inputs to cosmology. It has really played important role in the development of modern cosmology, and examples are CMB, galaxies which are bright in radio and 21 centimeter radiation. And as I was trying to impress upon you, future radio telescopes, I concentrated on the 21 centimeter part because it's basically happening at low frequency where India has a lot of interest. They will have important application in cosmology, but the same thing will happen in, for example, CMB as well. Okay, there's a lot of new missions being planned in CMB, and they will also do a lot for cosmology. Okay, so I will end here, and if there are other questions, I can take them. Thanks for listening. Yeah.
When the CMB was originated,
Yes.
we said that after the protons and neutrons started to fall into potentials and started forming atoms, the photons were freed and they were not.
Not potentials in the sense. You need. So there's a binding energy, right? Now what happens is if you have energy, so if let us say photons have energies larger than the binding energy of, then they will dissociate immediately. It will ionize.
So, like, this process was a continuous process, like the plasma is slowly forming atoms.
Okay. It is not. It happens very quickly. So the universe goes from ionized to neutral in a very short amount of time, and this happens because of something called Shah ionization equation. Okay, the way it works, and there are exponential factors sitting there. So what happens is basically you're basically keeping it ionized because of the tail of the black body radiation. You have a lot of photons. Okay, now suppose the energy is, let us say, okay, so let us take a step back. So the binding energy of hydrogen atom is 13.6 electron volts. If you convert it into temperature, it will be 10 to the 4 Kelvin. However, when the universe was 10 to the 4 Kelvin or slightly less than 10 to the 4 Kelvin, okay, let's say 9 into 10 to the 3 Kelvin, universe won't get neutral because most of the photons are probably less than 10 to the 4 Kelvin, but the tail, the black body has a tail, the exponential tail, that has enough photons to keep it ionized. So now what happens is you have to really go and decrease the energy of those photons in the tail. But since they're exponential, once you go and start hitting that tail, they go down very quickly. Okay, so this happens at a very short time scale. Okay, so the universe goes from ionized to neutral almost like at one redshift. Okay, there is a width, but that width is really small. Okay, so it's not like it is not happening over a million years or something. Okay, it's really happening over timescales of years or 100 years. Yeah.
Like, because if it would have been a continuous process, the photons would have
Yes.
ended over a period of.
Yes. No. I mean, it goes from predominantly ionized to predominantly neutral in a very predominantly neutral in a very quick time. There is always a residual ionized thing remaining, but that doesn't do much. I mean, the scattering is really negligible. Yeah, sorry.
Why does reionization occurs due to galaxy formation?
Yes, so what happens is galaxies will form stars. Okay. Now, if those stars, the stars will emit radiation. Now, if that radiation contains photons having energies larger than the binding energy of hydrogen, it will start ionizing the hydrogen. Now, this happens in the galaxies all the time. The question is, can it do to the kind of intergalactic hydrogen as well? So can they come out of the galaxy and ionize the surrounding and then the whole of the universe? So we know from other observations, non-radio observations which I did not talk about, that the universe today is ionized. Okay, so there's no doubt about that. This intergalactic hydrogen is completely ionized. Okay, so this is known and there's no confusion about it, but we don't know how and when it got ionized, and that is where all these reionization studies are going on. We have a good idea now, but with the 21 centimeter, it will be a direct probe of reionization. Yeah. Anything? Yes.
Sir,
Yeah.
do we know very precisely when the epoch of reionization was?
No. Unfortunately, no, because we don't have any direct observations. Okay, so we have some idea. So reionization, there are various things it does. Okay, so for example, think of the CMB. I'm constantly making the point that the CMB originated because the universe got neutral. Now, suppose you ionize the universe again, that will affect the CMB in some way. So it indeed does, and it does in various funny ways. It is difficult to explain here because there is a lot of physics involved. But what happens is it gives rise to polarization because the Thomson scattering starts again, and it gives rise to some extra polarization, and that's a very useful way. So this is, for example, the polarization power spectrum. You will see a bump here. This bump is arising entirely because of reionization. If reionization weren't happening, this would just go something like this, flat. Okay, and this bump arises because of So this gives an idea about when reionization occurred. The problem is CMB. Whatever we do, it's an integrated effect. Whatever we observe it as an integration basically from when it originated to today. From here, we get some idea that reionization, maybe the midpoint should be somewhere around redshifts of 8 or 7 or so. Okay?
So the point I'm trying to make here, then we also know that reionization is due to galaxy formation.
Yes, so as I am saying, we don't.
Separate fact, the time when galaxies.
Right, that is the idea, but that's what I'm saying. We don't know precisely. So that's one. So CMB is telling us that the midpoint is somewhere around 7 or 8. There are other sets of observations which have to do with quasar absorption systems. That tells us that the reionization probably completed somewhere around 5.5. Okay, but then it must be an extended process. So now it would have started before 8, but now whether it started at 12 or 17, we don't know. Okay, so there we need some extra handle. Okay, and that's where the 21 centimeter will play a role. Yes, so but once we have that handle in hand, then it is good. I mean, then we know that around that time the first galaxies would have formed. On the other hand, if we, for example, detect this signal, the 21 centimeter signal from cosmic dawn, what I was trying to show here, if we detect this signal, that will also tell you when the first galaxies formed.
It shows like it's around 20 redshift.
No, this is the model.
Okay.
This is a model which has been used to plot. There is no data here. Once the data comes, only then we will know.
If we are modeling, we should have some references for the modeling. Right?
Those are the references. That it is midpoint is somewhere around 8.
We are doing like for 20 because first galaxies are forming beyond 20 redshifts.
In this case, it is somewhere around 30 or so. But this is, as I said, this is just a model. I mean, there's no reason to believe that this model is correct. Okay, but yes, I mean, as I said, we know that they must have been forming before 12 or so. Okay, otherwise getting the CMB observations would be difficult. But yeah, how much before that is okay. Then there are other observations which are, as we speak, are coming up. That's coming because of JWST. Now, JWST is throwing up candidates at redshift 16, 17 and things like that. Now, how many of them will be confirmed, we don't know. Okay, but that is an additional thing. But that means, so JWST is probably giving us some very bright galaxies at redshift 16. So maybe then the first galaxies formed at much earlier times. Okay, so then maybe this model is correct. We don't know.
At the moment, like we have found like at the paper it was like 10 redshift. Like we have basically discovered about the properties of the 10 redshift galaxy.
No. Okay, 10 redshift galaxies where we have solid kind of evidence with statistics. But JWST has detected galaxies with potential redshifts at way beyond that. Okay, 12, 13 and so on.
Have we taken the like?
But we
analyzed it. Have we?
No, we don't have what we call spectroscopic confirmation of that. Yes. So the highest redshift confirmation is 11 point something. Yes. But yeah, these are candidates and some of them might be true. So we don't know. Yeah.
So how does the correlation function help us to find the probability of finding a galaxy?
Yes. So basically what you are doing is, so suppose you are, let us say I am standing here, okay? I mean, think of us as cosmological scales, and I take a ruler of some size, okay? And I go and measure how many galaxies are there. Okay, so I measure how many galaxies are there at that distance relative to me, and I compute that number, okay? Now, if the distribution was completely random, then I would have theoretically would be able to calculate how many galaxies I expect to find at a distance. Okay, so I will take a ruler and then I will create a spherical shell around it, because exactly at that distance I may not find anything, right? So I say I take a ruler of 10 megaparsec and I create this shell of, let us say, 1 megaparsec or so. So I have created a spherical shell. I find out how many galaxies are there with respect to me. Okay. Now that will give us a number. That is basically the correlation function, a measure of the correlation function. However, if it is completely random, I know exactly how many galaxies I expect to find within that. Okay, because I know the mean number of galaxies in the universe, let us say, and so roughly mean number density of galaxies times the volume of that shell will give you the expected number of galaxies in that shell. Now whether I find more or less than that tells me whether that basically gives you the probability. Okay, and that a theoretical model or our understanding of the universe will also give that probability, in the sense the fact that our universe, everything is not random and there are some things happening at some scales and some things are not happening at some scales, that basically predicts this correlation function. Okay, so that's why we can connect the theoretical model predictions with observations. So that is why the correlation function is a very crucial thing for measuring fluctuations.